Okay, so acids and bases. Oops. Maybe I should spell it properly. Acids and bases. And I'll just put this in here. Another word for bases is alkalis. So sometimes you see alkalis. It's probably not an apostrophe. Okay, so acids. Let's start with the properties of these things and then go from there. So it was noticed in ancient times, there's a class of chemicals and they all share certain very similar properties, okay? So let's talk about the properties of acids first. And so the first thing that most people learn when they learn about acids and bases is they learn that acids have a sour flavor. Okay, now, certain acids are fine to eat, they're edible. However, any lab acids, we ask that you never ever put them on your tongue, because another property of acids is that they tend to be corrosive. Okay? Which means they can cause chemical burns to your skin. That doesn't mean that any acid you come across is going to have enough concentration to burn you. In fact, you can dilute acids down until they're, able to be used as, say, food flavorings, for instance, or vitamins. However, the labs we have in acid, the acids we have in the lab tend to be not something you want to ever get on your skin. Okay. 3, they tend to dissolve metals. We did an experiment there a little while ago where I dissolved some magnesium metal, or actually I think it was zinc metal, can't actually remember, into hydrochloric acid, and we saw that it produced a lot of bubbles and so on, and we'll talk about what that reaction is as we go. Sour flavor, corrosive, dissolved metals, they have a low pH. I'll talk about what pH is in a little while, and that pH is lower than 7. So we'll talk about the pH scale of acids and I guess bases in a little bit. And a little bit about their name. The name acid means oxygen forming or oxygen containing. And that's because early scientists thought all acids contained oxygen. And we'll see that that's not actually true, but many do, okay? So these are the properties of acids. So I think what we'll do is we'll go right through what acids are now, and we'll go back and do the properties of bases and what bases are, okay? And we'll talk a little bit about the theory behind acids and bases. So what is an acid? We sort of discussed it last class. Does anyone remember what an acid is? I would know something's an acid if we say we're to look at its chemical formula. Here, I know what I'll do. I'll write out a few famous acids, and we can sort of start to compare what's common or similar about them. If you have a question, just hold on one sec. I'll just write a few out, and then you can probably answer that question after this. So here's some acids. Okay. So there's a few acids. And you can see the 3 of these that I drew do contain oxygen and 2 don't. the vast majority of acids are of this type because the vast majority of ions are polyatomic ions, and pretty much all polyatomic ions contain oxygen. Not all, but pretty much all. Okay? So what do you see in common for things that are acids? Hydrogen. Good. What type of compounds would you classify these at if you were just to look at them? What do they contain? Something from the left side of the periodic table and something from the right side of the periodic table. Okay? So they all have an anion, right? So there's a fluoride anion, chloride anion, a nitrate anion, a sulfate anion, and a phosphate anion, right? There are basically, anytime you put a hydrogen with an anion, okay, it's going to make an acid. So what do they have in common? They all have hydrogen as the cation, right? So some acids, what do they do? What do they have? What's all in common on them? They have hydrogen ions as the cation. So what are they? They're ionic compounds with hydrogen as the cation. Okay, so all acids are ionic compounds with hydrogen as the cation. Okay. Are we good? Okay, let's run through bases, and then we'll bring it all together. So bases. First thing is that bases taste bitter. Okay. And again, like with acids, you don't want to be eating bases if you can help it. Bases, they tend to also be corrosive. In other words, they can burn your skin, and they're also very good at dissolving organic compounds. So one use of a base is as drain cleaner, for instance. So Drano is a very strong base, and usually drain clogs are things like hair and body oils and so on. So you dump base down into your drain, and it starts to dissolve up that matter. So obviously, for obvious reasons, you don't want to put that onto your skin. It feels slippery. The reason I've heard for that is because they're involved in a reaction that starts to convert fat into soap. So the oils, I guess, on your skin tend to be turned into soap, or start to be turned into soap anyway, and that gives that slippery feeling. If you touch a liquid and you're not sure what it is, and all of a sudden your fingers feel slippery, it's likely that it's a base, and you want to get it off your hands as quickly as possible. Okay? Bases, in terms of pH, are high. Okay, so higher than 7. Okay. Last but not least, we can, what else do I have to say here? The name. So, the word alkali comes from Arabic, and it means ash or ashes. And the reason why is because the ashes left over after a fire tend to be very basic. Okay. So let's write out some bases, and we can sort of start to see what they might have in common. Now, bases are a little bit harder to spot. Some of them don't actually really look like bases, but we can explain why they're bases a little bit down the road. So here's a couple. So what do you notice about the bases? They also contain hydrogen, yeah, that's right. Specifically, look at this. I'm going to skip this one because it's not exactly part of the gang, but 3 of these 4 have something very, yeah. Okay. Right? So let's focus on the first part that you said. So they all contain this OH anion. Okay. First of all, what type of compounds are these 3 here? What type of compounds are they clearly? They have to be what type of compound? Why do they have to be ionic compounds? Right, they all start with a metal. Just skip this one for now. We'll talk about why it's a base in a minute. But yes, in general, bases are going to be ionic compounds. Okay, they are going to contain a metal on the left side as a cation, and they're all going to contain as an anion this anion. What is this anion called? Hydroxide. Excellent. Hydroxide. Now, what did we say after that up here? Okay, right. So we'll just write that down. They don't all have hydroxide, but they tend to have hydroxide as their anion. All right. Hydroxide is their anion. So let's examine this a little more closely here. Let's take an acid, let's take a sample acid here, and we'll grab this one. Okay, there's a sample acid. Let's grab a sample base. Let's just pull them apart and see what is going on there. So let's imagine that this is in aqueous solution. What does that mean again? It's an aqueous solution. Great, it's dissolved in water, absolutely. So let's look and see what would happen if we took an HCl and we dissolved it into some water. If we dissolved it into water, what would end up happening, so let's say right here we have a big, holy, I'm using my straight line drawer, that was brutal. We'll make ourselves like a beaker here. Perfect. So here we have a beaker full of water, and what we're going to do is we're going to put in some hydrochloric acid. Okay? What's going to happen when this enters the aqueous solution is it's going to dissolve. When something is dissolved in water, what that means is that its ions split apart and freely float around. Remember how we said that ionic compounds dissolved in water created electrolytes? Can someone remind me what an electrolyte can do? What can an electrolyte do that regular water can't do? Front row. Front row. Electrolyte, what can it do? There was the light bulb thing. And how did the light bulb thing work with an electrolyte? That's the key. It allows water to conduct. Okay? It allows water to conduct. So, inside the water, there must be something added when we add an electrolyte that allows the water to conduct. So what's going on there is this ionic compound is actually splitting into its parts, right? So what we'll end up with is a solution in water, in normal water, that then has extra H pluses in it that weren't there before, okay? That weren't there before. We'll talk about the importance of that in a minute. So this would actually be an electrolytic solution. Once we add some acid into water, these ions allow charge to transfer between, say, 2 electrodes that we might place in here. Okay, so this has become an electrolytic solution now. So what we're going to do is we're going to do the exact same thing, but we're going to look at what's going to happen with a base. I think you'll be able to see pretty quickly that it's a similar situation. And what we're going to eventually arrive at is a conclusion about how acids and bases are related and their relationship with water. So into here, we're going to dissolve this other ionic compound. And what's going to end up happening is it's going to be adding extra hydroxides into the water. Okay? So what we have to realize is this is just one type of acid, right? If we had other types of acids, like say we had some H2SO4, or we had some HF, we had some HNO3, okay? If you look, the anions would be different, but they're all going to add H plus into the solution. No matter which one of these you add, H plus concentration is going to go up. Yeah, you have different anions, but that's not important. What makes something acidic in character is the fact that it adds H plus to solution. Okay, so acids add, so they all contain H plus, they add H plus to solution. Okay, so no matter which one we put in there, same scenario. H plus comes off as an ion and adds it to solution. And look at this one. For every one of these we add, we get 2 H pluses, right? So that's kind of interesting. Same over here. Oop. Let's keep our color consistent. If we look over here, what if we added like AlOH3 to that solution? Okay. Actually, I think I forgot to put the. Okay, I did that right. Oops. Let's just fix this. There. That's better. Sorry about that. I forgot brackets up there. I just realized. Okay. If we add this base instead of this base, we're actually going to get 3 times as much OH for every ionic unit of this we add, okay? So there we go. So what's the key to this? Well, bases are adding extra OH, no matter which one we put in there, okay? Now, before we get to our big reveal here, bases add OH minus to solutions. They're ionic compounds that when you dissolve them, they add OH minus. Okay? So a better way to put this, right? A way to say this is to say, another way to say it is they raise the concentration of the ion of interest. Okay, so that's important. Now what I want to do is I want to examine what happens if we just look at H plus and OH minus. What does that look like to you? What if we put these together? What would you get? If you put H plus together with OH minus, that makes water, doesn't it? Okay, now do we normally think of water as being an ionic compound? We usually don't, right? We usually say water is a molecular compound. And for the most part, water actually is a molecular compound. So if we look at water, we draw a picture of water, generally what we would think is we'd think, okay, so in water, we have a setup like this. Here's an oxygen, right? Okay, then that is bonded with 2 hydrogens, like so. Okay, and so this is our chemical workup, our Lewis workup, if you want, of what water what we tend to consider water to be. Okay, I don't want to get too deep into the chemistry here, but oxygen is an atom that has a very strong attraction for electrons, okay? So what ends up happening is this oxygen pulls the electrons that are shared here towards itself, And that leaves a sort of a more positive charge over on the ends here, okay? And what that actually does is, if you think we might have like we might have a container of water, and let's imagine that, and it's a little bit hard to do, but let's imagine that you're adding adding water in here, okay? And water in this case is going to be actually interacting with other water, and essentially the positive parts of the water molecules are going to pull the other water molecules to some extent into ionic parts. So what ends up happening is this. So if you think of a water molecule, let's just clear the area here. It's a little bit hard to understand, but let's just see if we can do it. Let's imagine we have, this is actually also the reason why ionic compounds dissolve in water to begin with. It's because it's got what's called polarity, okay? So because this oxygen attracts the electrons towards it, it ends up with kind of an overall sort of negative charge, and the hydrogens end up with an overall sort of a positive charge on a single molecule. We call it a polar molecule. And the ability that a polar molecule has is to, when we say introduce something like HCl, actually pull the H plus over to this and the Cl over to that, and actually pull it into solution. So the reason why water can dissolve ionic compounds is because it's what's called a polar molecule. And that doesn't exactly explain what we were talking about when we want to think of water as an ionic compound. However, imagine if instead of thinking of water, we think that some water might behave like this. So let's imagine that, you know, this is behaving as an acid, and this is behaving as a base. You will actually get a little bit of water essentially dissolving itself into ions. Seems weird, but a little bit of all water is actually split into two ions rather than existing at molecules. So what does that mean? So what that means is, in normal water, very little bit of the water exists like this. Okay, a tiny little bit. And this is going to be a little bit confusing, but the concentration of H plus and OH minus in normal water equals 1 times 10 to the negative 7 moles. Now we haven't introduced the mole, don't worry about that. Moles per liter. Okay? What this is saying is, this is a way of talking about an amount in chemistry. You don't have to get too concerned with it, but what I do want to point out is this negative 7, because that's super important. Now, have you guys learned about logarithms? Okay. I'm going to teach you logarithms really quickly right now. Yeah. Yes. So we're going to pause for 1 second and catch our breath. So to understand the pH scale, we need to understand logarithms really quickly, okay? And then we'll come back and we'll wrap it all up. So what's a logarithm? Well, a logarithm is a number that you must raise 10 to the power of in order to get it. Now that is probably not the best way to describe it, but I'll show you by example, okay? So here's an example. Let's say we have the number 100, okay? Now, 100 is equal to 1 times 10 raised to the power of 2. Do you know that from math class? Which is equal to 1 times 10 times itself. Okay, are you with me? 1 times 10 squared is the same as 1 times 10 times 10, right? Squaring 10 is just multiplying by itself twice. Yeah? You with me? Now, if I were to say log of 100, the answer would be 2. Because I have to raise 10 to the power of 2 to get 100. So the log of 100 is 2. Make sense? Let's try another one. What is the log of 1,000? Well, to get 1,000, I need 1 times 1,000. Or 1 times 10 times 10 times 10. Or 1 times 10 to the 3. Oops, I kind of stuffed it in there a little bit. So the log of 1,000 is 1 times 10 to the 3. Okay? So it's got to be, what do you think? Yeah, there it is. 3. So logarithms are actually pretty easy. Okay? What do you think the log of 1 million is? Oh yeah. Is it just how many zeros? Yeah, essentially, really, that is what it is. Sort of. Okay? I don't know if you should default to it's how many zeros there are, because the zeros represent something, right? What they represent is that this is 1 times 10 to the 6th. The log of a million is 6, because in order to get a million, you have to raise 10 to the power of 6. Okay? Could you do a logarithm for a number that is not equal to 10? Or not a multiple of 10? Hey, Tyler, Rory, learn something new, boys. Pay attention. Okay? So what if I wanted to do the log of 200? One sec. What if I want to do the log of 200? Who has a calculator on them? Grab out your calculator. Do the log of 200. Would not be 4. What you have to understand is it's 1 times 10 to the blank equals 200. Can you do something, raise 10 to some power, such that it equals 200? You probably can't do it in your head. So if you raise 10 to the power of 2.3, you get 200. Okay? So you can do the log of a number that is not full, like there's not a multiple of 10. Okay? But in this scenario, okay, we are dealing with numbers raised to values here. So where does this come in with pH? So we understand then that the log of a number is the number you have to raise 10 to the power of in order to get that number. So to get 100, you take 10 and raise it to the power of 2. To get 1,000, you take 10 and raise it to 3. To get 10,000, raise it to 4, and so on. To get a million, you raise it to 6. So the logs of these numbers are just those power values that you raise 10 to. Okay? That's the concept of a log. pH is a negative logarithm. Okay? So pH is the negative logarithm. Trust me, this will all come together in a minute. Negative logarithm of the concentration of H plus ions in solution. Okay, let's examine this pH symbol here. Well, the little p is used in science, and it means just the negative log of some value. So in this case, it's the negative log of the H plus concentration. You'll learn more about concentration in moles next year, okay? But what's important is what that does to the concentration. So remember we said in normal everyday water, in just water that you pour out of your tap, I guess as long as it's distilled tap water has some of its content in terms of H plus. Just a little bit, tiny little bit is like that. The rest is regular, everyday, normal water. So if we look at that concentration, it turns out that there's 1 times 10 to the negative 7. This new term, which please don't really worry about, is just a way of quantifying an amount of this, which you'll learn next year. But in order to explain pH, I need to use this term, unfortunately. Moles per liter. Okay? Now, if I take the negative log of this value, okay, let's first look at what the log of it is. What is the log of 1 times 10 to the negative 7? What value does that give you? What did we have to raise 10 to the power of in order to get this number? It's right there. What is it? Negative 7. So the log of 1 times 10 to the negative 7 is 7. Or sorry, it's negative 7. Sorry. It's just like if we did this. What is the log of 1 times 10 to the 7? It's the same as saying, what is the log of 10 million? Well, the log of 10 million, that's 7. What's the log of 1 million? Negative 7, because you got to raise 10 to the negative 7 in order to get that. Okay? Do you understand what this number means? Do you get what this number means? Do you understand it? You learn it in math class, what this means? So what it means is this. It means, this number means this. I'll write it out in whole, and then we'll just look at it. So 1, 2, 3, 4, 5, 6. I think I put one too many in there, didn't I? Oh. Yeah, I did. Oops. Okay, so that's what this number means, right? It's a little number. So a way to get that would be, is the same as saying 1 times 1 over, so here's how this works, right guys? Here's tenths, hundredths, thousandths, 10,000ths, 100,000ths, then millionths, and then 10 millionths. And sorry, it should be 7. 7 times 1/10 millionth. Okay, well another way to write 1/10 millionth is like writing this. 1, 10, times 10, times 10, times 10, all the way 7 times. And another way to write that is this. Okay, another way to write that is this. There, math class done. So 7 times 10 to the negative 7 is this number. That's what this number means. The logarithm of it is negative 7, right? I had to multiply 10 by itself 7 times in order to get this tiny little number. All right? Are you with me? So far, so good. Now, we said pH is not the log of this, but it's the negative log of that. So what's the negative log of 1 times 10 to the negative 7? It's the same as saying, what is negative 7? It's just 7. Okay, so what are we saying? We're saying then that the pH of water is equal to what number? 7. Have you ever heard that before, that the pH of water is 7? You probably have. They like to use it on like commercials for like bath products and stuff, or makeup, right? They always say the pH is pH balanced, or it's pH, you know, matched to your body chemistry. Which is around 7, not quite exactly 7, but close to 7. So that's what pH means, okay? Now, let's wrap it all up. So, long story short, water has a pH of 7. Get what pH is, rewind, and watch it again. So water has a pH of 7. Acids add H plus ions to water. So let's see what that's going to do to the pH. So let's say we have regular old water here. Okay? It's got a few H pluses, but not very much. Okay? It's got 1 times 10 to the negative 7. We won't worry about units right now, but it's got that concentration of H plus in it. Okay? Now let's say we take some hydrochloric acid and we start adding it in. Look at what happens. Every HCl we add puts another H plus into solution. So as we keep adding it, and as we keep adding it, this number's going to start changing, isn't it? The amount of H plus is going to change. Eventually, we might add so much that we get to this value. Okay? What we've essentially done is we've increased the amount of H plus by 10 times, right? 10 times. So now instead of 1/10 millionth, we've got 1/1 millionth concentration of H plus in there. Now remember, the pH of this is 7. What would the pH of this be? 6. What if we added so much that we got to this? What would the pH there be? Right. So as we keep adding H plus, what that does, by consequence, this number goes up. Remember, being less negative is the same as getting larger, right? -7 is a smaller number than -2, and 0 is a larger number than -1, right? Does that make sense? So as we're adding H plus, look at our pH. It's dropping, okay? So adding acid drops pH. Okay? You can just memorize that. If you don't care about understanding it, you're not going to continue on in chemistry, okay? It's fine to just remember that as you add acid, pH gets lower. If you are going to continue on in chemistry, it's good to know this. It's an important property of acids and bases, okay? So on the other hand, all right, let's imagine that we're adding OH, right? Turns out there actually is a unit called the POH. We don't often use it. So what's going to happen is, let's say we take our normal water and we start adding OH into it. So what we think about then is we think that these new OHs, what they're going to actually do, how they're going to behave, is they're going to take the natural H plus that was in water and they're going to pair off with it. So what they're going to start to do is they're going to reduce the amount of H plus that is in solution, right? So when we start, before we've done anything, right, we haven't added any OH yet, we're at a pH of 7, right? Just like we were before. But now we're going to reduce the amount of H plus, right? So now it's going to go to like -8. Okay, well, our pH is now gone to 8. If we keep adding OH, it's going to keep sucking and pulling H pluses out of solution. Then our pH is going to continue to rise up to a maximum of 14. Okay, so this is how acids and bases adding to water changes the pH, and why normal neutral water has a pH of 7. Okay, lower pHs equal more acidic, less H pluses equal more basic. Okay, so the pH system goes from 1 to 14. Anything on this side of 7 is an acid. Anything on this side of 7 is a base. Are there any questions?